Okay, do you see recording?
Yet.
Okay, fantastic. So hello everyone, and welcome to the QRISE 2024 QuEra Computing Workshop. QuEra's QRISE project proposal involves creating a compilation visualizer for neutral atom gate-based quantum computers that incorporates the novel capability to shuttle atoms between different regions of the processor during the course of computation. This workshop will be important for understanding the scope, motivation, and the particulars of this challenge. To lead this workshop, we're very fortunate to have Pedro Lopez, a quantum physicist who serves as the lead quantum advocate at QuEra Computing. Pedro received his PhD in physics from Universidad Estadual de Campinas in 2016 and went on to be a postdoctoral research fellow at Institut Quantique de l'Université de Sherbrooke. Since then, Pedro has served as a project manager at Stuart Blisson Quantum Matter Institute and a quantum computing consultant at Physical Sciences Innovations Corporation. Pedro continues to pursue research, including theoretical and numerical investigations of quasi-particle fractionalization and the emergence of symmetry in strongly correlated quantum matter. I've also had the privilege to work with Pedro personally, and I can add that he likes Irish music and is great at playing the fiddle. With that, I will turn the floor over to Pedro. Thanks so much for being here.
Thanks, Ben, for the intro. That's too kind. And hi, everyone. I hope we are going to have a great time here. As Ben mentioned, the goal of this workshop is to equip you a little bit with the tools and the information necessary for you to try to tackle our challenge for QuEra, for QRISE. We're very excited. This is going to be our first time engaging with folks from outside of QuEra on topics related to gate-based quantum computing and error correction, etc., etc., etc. So let me, without further ado, share my screen and get to business. So there we go. QRISE 2024 Intro Workshop. I don't know how many of you have heard of neutral atom quantum computing, but I believe that we have made a lot of noise in the past 2 years, and I would be surprised if neutral atom quantum computing is still seen as a emerging and mostly not known technology for developing quantum processing units. I do remember, though, that 2 years and a quarter ago, more or less, when I started this, talking about neutral atoms for quantum computing was a rare thing. And what got us excited and has shown to be indeed the case is that this technology allows us to pack a lot of qubits together. These are atoms, they're not ions, they don't complain for being close to each other. There is very efficient control schemes, which is extremely important for scaling the systems up in a practical manner. And there are very, very flexible ways of encoding problems. And generally, this is a platform that is special because it allows you to think about quantum computing in new ways, more flexible and more autonomous ways. I hope to, through this talk, give you a little bit of a feeling as to why this is the case, and to guide you again with the mindset, right, of what we are hoping to see you accomplish in this challenge. So the main theme of the challenge is actually the main theme for QuEra and our closest collaborators for the next quite few years, right? So we had a roadmap show last January, where we have announced that we'll be building quantum computers capable of operating several logical qubits. And the point with all of this is that doing gate-based quantum computing without a clear path for error correction is not really a meaningful way of building scalable quantum computing. Okay, so you cannot avoid error correction. On the other hand, most of the applications that we have seen so far, they have been always focused on kind of looking at the theoretical path in separate from the hardware path, doing these things in parallel, but not in very much synergy. What I have been looking for is to foster the community to start thinking more deeply about co-design, right? So you have an algorithmic pipeline, you have hardware capabilities that are native, and you need to start thinking about how do you choose your algorithm, how do you choose their compilation, how you choose the gates that you design, how do you create the layout for your algorithmic protocol and choice of error correction code in a way that makes the best use of the specific capabilities of your hardware. Some hardware might be faster than others. Some hardware might have a different connectivity than others. In our case, we have to take into account the speed, the qubit connectivity, the capacity to parallelize operations, what is the universal gate set that we have, and how to make best use of the noises that exist in the system. Can you erase those noises? Can you leverage the fact that it has a structure that is tied to the hardware? We believe at QuEra that the only way to achieve operational quantum computers is to co-design the hardware and the algorithmic pipeline. Now, you can see on the right side that there are many, many features there to take into account. And this means that your design space is huge, right? So if the design space is huge, this means that this is a very, very non-trivial problem. And the goal of this challenge here at QRISE is to help our developers, more on the right side of this cycle, if you want, to be able to approach this challenge, this task of co-designing algorithms and with the hardware capabilities in mind in a more intuitive way. And for intuition, sometimes visualization helps. And I think that we are thinking about reporting tools, we are thinking about imaging, and so on and so forth. With the context in place, let's start talking a little bit of why this is important. Here's an example of what can be achieved if you do this design correctly. This is a demonstration on a paper that was released by our collaborators at Harvard in December last year. QuEra was deeply involved in enabling this work to happen. And what was happening here is that we were designing logical qubit operations for complex circuit sampling. So if you followed the Google quantum supremacy demonstration for 4 or 5 years ago, it's hard to think that it's been so long. Those were demonstrated with kind of natural, isolated, individual physical qubits. Here, what we were doing was to use a type of 3D cubic code that's called an 832 code to encode logical qubits, so therefore qubits that have a better performance for operation than the individual ones. And we did 48 of them. 48 of them because we know exactly what the hardware looks like. We know exactly what kind of protocols are the best. And we encoded these 48 qubits. So this is on the left, the top left here is what the code looks like. This figure C here, let's look by row. It's pretty much what the actual protocol in terms of gates looks like. So you can see that this is a very complicated and it includes connectivities and C naughts and CZs technically between qubits that are quite far from each other. But yet it was able to demonstrate things like this. So this bottom left figure here is showing what's known as a Porter-Thomas distribution. And what you see is that this is you expect from some this complex sampling type of problem that was being studied. And you have the gray figure on the back, that's theory. And as we increase the capacity to detect errors on these logical qubits, you see that this sample or this distribution here gets closer and closer and closer to look like exactly what the theory expects. Meaning the more we correct errors, the better the performance of the system. So this was a major demonstration, pretty much because previous demonstrations of operations of logical qubits, I guess from last year, we're looking at 2 logical qubits, and this is like a 48 all at once. But it was only possible because we really knew what the hardware capabilities are and how to design the experiments to our, in alignment with that. So the key set of information that I can bring you to help you with try to achieve or succeed in this challenge is to help you understand a little bit what are these hardware capabilities and what are the features or constraints that we would like you to keep in mind and to enable people to think about when designing their algorithms. And for that, we need to start slowly talking a little bit about computer architectures and also quantum computer architectures. On the top left here, what you see is a processor. Many of you might have seen a processor. Many of you might have broken a computer open just to take a look at it. But if you didn't, this is what it looks like. Now, even though when you look from this direction, or from this distance, this thing looks quite simple and monolithic, when you look deep inside, this structure that looks just a bunch of dots is actually highly functional. It's not homogeneous at all. It's not monolithic at all. It has areas and pieces that have very specific duties, if you want, in the operation of the processor. And our mindset here at QuEra is that it shouldn't be different for a quantum computer. Okay, a quantum processor should not just be a bunch of qubits, but rather it should be something like this, where each dot here is a different qubit, but we have different zones, right? I hope you can see the analogy between what you're looking at the bottom left and the top right, or the entire right part of this figure. There are areas in your processor that are good for storage. There are other areas that are good for entangling. There are other areas that are good for readout, and they should not be mixed, because operating qubits is always paradoxical, right? You want your qubits to be as isolated as possible, because you have to fight the decoherence, but at the same time, you have to interact with them. If you don't interact with them, you can't do calculations. So you need to make them an area where they are protected, like this storage area, separated from an area where you are actually playing with it. And this type of mindset has been possible through a series of papers, and I'm taking the chance here to introduce you a little bit. The references are not complete, but they should be easily, easy to find in our GitHub repo for the challenge. But yeah, this has been the mindset that we've been taking. Qubits on a neutral atom so far have been done by puffing up atoms. So if you have been around us in any way, you have seen our conversations about analog computing. You know that at QuEra, we have been focusing on using rubidium atoms so far. And that rubidium atoms are like hydrogen. They live in the first column of the periodic table. It has one valence electron. It can be in the ground or the Rydberg. And the beauty of the Rydberg state is that when they are in the Rydberg state, we have an interaction that decays with the distance between two qubits to power 6. And then we can put a lot of qubits together, and then we can make them talk and entangle and et cetera, et cetera. Now, the problem is that this Rydberg state is actually very sensitive. And when operating gates, we are doing something completely different. Now we are not operating qubits, but something that is closer to qubits. So there are 3 levels that are important: 2 ground states, we call them hyperfine splits, and 1 good entangling state, the Rydberg state. And the idea is that the ground states here, this hyperfine split qubits, they are quite isolated from the environment and really, really protected, while the Rydberg state is still, well, and because they are isolated, of course, they have long coherence times, they are high stability, and they are highly flexible in the sense of being you're being able to shake this qubit around and not degrading your information, as we'll discuss in a second. But we still use the Rydberg states for having strongly controlled interaction. So this is, in some senses, the best case scenario, right? Your qubit is only on when you want. Remember what we're saying. We're saying that qubits have to be isolated, but we have to be able to interact with them. So the qubits are always the qubits, but as long as I don't excite them to the Rydberg state, they are isolated. Whenever I want to talk to them, I excite them up, interact, and then push them down again. And then they remain, with the information inside this hyperfine split. Everybody's protected. That's the cool thing. So this is the basic structure of operating gate-based quantum computers with neutral atoms as we see it. What the architecture looks like now is something like this. We use the fact that this isolated qubits, these qubits in the hyperfine states, 0, 1, they are so robust that we can actually move them around without losing entanglement. And the coherence times that we have for these guys are over 1 second. And you see here an example of generating entanglement. So to entangle qubits, we have to move them side by side. Remember, from this figure here, that's to entangle, we need to have qubits close to each other because the interaction goes with the distance to power 6, 1 over the distance to power 6. And now we can entangle qubits and move them apart like this without losing the entanglement. So this is a little operation of parity here between the qubits. So we apply this pi over 2 pulse, and we look at our capacity to entangle with qubits just staying close together and measure, or entangle, separate them and measure. And what you're seeing here is that basically there is no distinction between keeping the qubits close or letting the qubits go far from each other, meaning we can transport information inside our quantum system without degradation. Of course, this depends on how fast we go. So this is what this other panel is showing. But you can see that qubits can move at a 0.4, 0.5 micrometers per microsecond and really cover an area that is quite large, right? So the coherence times are over a second. We are moving at micrometers per microseconds. We can really go around like a few thousands of qubits within this coherence time multiple times. The single qubit gates that we have, so you can see here, they are just achieved by operating on these hyperfine states. The state that we mostly care about is a state that is magnetically kind of isolated. It's called an MF, right? So MF equals 0. So it's where the total angular momentum is basically well, it's the projection is vanishing. Therefore, it's not really sensitive to potentials around the atom, and we can do operations in a single qubit at 99.99 fidelity. Let's talk a little bit about the 2-qubit gates. So 2-qubit gates, there are several ways of doing them, and in particular, there was a demonstration last year from, again, our friends at Harvard, where they were doing what are called phase optimal gates. You're seeing what is the protocol. These guys are still using the Rydberg blockade, so nothing different from what I mentioned before. But the point is that you do 2-qubit gates using position, right? So atoms close together, you entangle, atoms far, don't entangle. And this is amazing. We can do 99.5 2-qubit gate fidelities. This is the natural gate here is a CZ gate. But something that is quite interesting is that because position is what is used to do entanglement, we can push harder. We can actually put atoms closer together, more than 2, and similarly perform 3-qubit gates natively in the system. And this is a figure that shows pretty much the gates time over in comparison with the coherence time for this for number of qubits increasing. But the point is that even for a CCZ gate, that is something that is usually achieved in most quantum computers by decomposing a 3-qubit gate into multiples of 2-qubit gates, we can achieve fairly high fidelity. 97.9% fidelity is what was demonstrated. So it starts to look that designing protocols here requires you to start to take considerations like, well, is it better to do 5 or 8 2-qubit gates, or to do a single native CCZ gate? Right, so these are the type of considerations that when designing protocols we have to keep in mind. So what are the native gate sets? Native gate sets for us are going to be controlled Z gates, controlled Z gates, controlled Z gates, and so on, so forth. The controlled Z phase gates, so it's actually possible to also not just do pi phases around Z, but do general phases around Z. And do things like permutation symmetric Z phase gate. So you can see that we have these states, and they're picking up phases without changing the permutation. Like within a given a given set of permutations here, like 001, 101, 100. They all pick the same phase, the next pick another phase, and the 00 picks a third phase. And finally, of course, arbitrary 1-qubit rotation. So whenever a user is thinking of designing protocols, they need to know what are these native gates and figure out how to make the best protocols, the best algorithms, and the best quantum error correction encodings that take advantage of exactly this native gate set. Let's talk a little bit more about entanglement transport. Okay, so again, we were saying that we entangle pairs. We amusingly and interestingly, we shine one laser and entangle all of them. Technically, it's two lasers. It's more. These are two photon transitions, but for all that you care, it's a single light beam that is affecting all qubits all at once, meaning that there is a high degree of parallelization here. And then you get these 2-qubit gates, and then you can move the guys apart and transport qubits are all around in less than 300 microseconds. Okay, so remember that the T2s that we have here are of 1.5 seconds, while the transport, the time that it takes to move across the entire arrays is of order hundreds of microseconds, which means that it's never about the T2, but rather T2 times 1 over the time that it takes for you to do operations. This is just a revision of what we discussed before, but again, stationary qubits and transported qubits perform basically with equal performance. And atom spacings are of about 3 micrometers. So this means that, well, here you go, right? So transport over arrays of 2000 qubits in times that are order 10 to the minus 3 times our T2, meaning that we can do a lot of reconfiguration of these atoms within our coherence time. Why do you want to do entanglement transport? So there are a few reasons. Reason number one is this one that you're seeing, right? Imagine that I have this set of qubits, and I want to generate an entanglement or swap between a qubit that's up here and a qubit that is down there. Now, if I have to do this on a processor that only has first neighbor connectivity, we are showing you on the right here what are the number of CNOTs that you have to apply to achieve exactly this swapping of information, right? And I think that we can all look at this and agree that this is a lot of 2-qubit gates. This is like an ungodly amount of qubit gates to perform one simple operation, which is exchanging these guys. Well, if you have reconfigurable connectivity, this is what you have, right? So you want this guy to go there and this guy to go here. Well, it's one operation. You just exchange them, literally, explicitly. So you can get much more mile for the buck, if you want, of your coherence, just because you have this capacity to transport entanglement with high fidelity. Okay, so remember that every 2-qubit gate that you apply induces errors in your system. Transporting induces much less error. The second reason why you want to do entanglement transport is because of your controls budget. So perhaps this is a little less relevant for algorithm design, but this is something that is important for people to be aware of. I think that this helps us think. On a classical computer, you have billions of transistors, but controls, they actually operate, they pretty much go on the perimeter of your processor. Okay, so order 1,000 external controls. So you have a ratio of what, like a million number of operating units, computation units, like transistors, to the number of controls, like a million operating units for one control. If you look at what exists today, and I'm picking here the state of the technology of superconducting qubits, just for an example to help us understand the challenge of scaling quantum computers, what you see is that right now we have 3 wires per qubit. So instead of a million of qubits per wire, we have 3 wires per qubit. Okay, and this is to control, like this means like hundreds of these high performance controls for experiments with 50 qubits. And you should also be aware that these wires are expensive. Okay, so one wire costing $1,000 means that if you are looking for things like applications like factoring 48 digits for RSA, this would require 20 million qubits, and this means that your quantum computer would cost $20 billion. So this means that a solution for this controls budget is very, very important. And what we have here is something called an AOD. We like our TLAs, our three-letter acronyms. So AOD is an acousto-optical deflector. These guys, they're controlled with pretty much one wire each, and they are capable of deflecting optics, acousto-optical deflector, via some vibration that you send into the system, no acoustic waves. So you can use these guys to move multiple atoms at once. So the number of controls here is much more interesting. Like we are looking at 5 controls for 50 qubits. So we are not at a million qubits per control, but we are in a counting ratio that is much more feasible and interesting for the platform. So when you are trying to design then your visualizers and etc., what do we expect you to have in mind? I think what we expect you to have in mind is such a sandbox model for this current generation of quantum computers. You should remember that this is the state of the technology today. Tomorrow it might look very different. So ideas for how we should change or revise this are going to be very welcome. But the idea is this, okay? So what are the parameters that go into your mindset, into your thinking? You should be thinking of systems that have hundreds to thousands of qubits. You should be looking at high fidelity parallelized gate operation with long coherence times. You should be looking at parallel movements of qubits on a grid. We are going to look at that in more details in a bit. You should be looking at systems capable of mid-circuit measurement and feed-forward. So there's some analogies to classical RAMs here, but these are these are the ingredients that go into the soup. And then you have to think, okay, with these constraints or with these features, what are the key thoughts or design choices that an algorithm developer or a compiler would have to think about in order to make the best use of this? Like this, is it the size of the zones, or is it like the geometric disposition? How do we move things around, etc., etc.? So let me give you the rules of the game then, right? So how would your users and our users be thinking of operating these guys? So we have 2 types of sites to hold atoms. These sites, they can be filled. So a site means that there's a laser beam shining somewhere. And this laser beam may or may not have an atom. Okay, so here what you're seeing is that pretty much every one of these guys is being held in place by an atom, but you could have a site where the laser is there and the atom is not there. So that's the case here. So whenever you see a guy with a little atom, that means there is an atom. The atom is a qubit. We will have, again, as I was mentioning, 2 types of sites. Sites that are fixed and sites that are movable. The sites that are fixed, they have to be completely, they can be positioned in an arbitrary way. So what you're seeing here is like, I don't know, this triangle, it's like a blob. But it's arbitrary, but these locations are fixed. Once it's defined, it's defined. We are not going to change that. Okay, the user doesn't get to change that. But then you have another set of lasers. These are the movable lasers. They're the lasers that are moved by those AODs that I was mentioning. Okay, and they can move vertically and horizontally, all of the sites in parallel. These movable sites, they will live in a rectangular array. Okay, so it's a rectangular array like you're seeing over there. And in this movable array, the rows and the columns, they move together. Rows cannot overlap. Columns cannot overlap. Okay, so they move together, but so you can distort, but you cannot kind of flip them. So that's an example. I'll do again for the effect. Ooh. There you go. So movable array, rows, columns move together. Rows cannot move over each other, but atoms can be picked up and dropped off between fixed and movable traps. So I can come here and drop my atom over there. And now this atom is fixed, stay in place. That's what's happening in the zone. right? So we have like that storage zone. I come with my lasers, I put atoms there. I choose some atoms that I want to interact with. I move them down to my entangling layer zone. I do my entanglement, I move them back, and I drop them. That's what this is showing. The compilation rules, and this is an interesting paper to look at it, is very interesting. So in principle, you would think that because I'm able to move these atoms all to all, I could have connectivity of all to all. But because of these rules of squishing and et cetera, what we have is actually something that we call efficient parallel swap. And efficient parallel swap means that we can swap gates in parallel, swap qubits in parallel, right? And efficiently sort these atoms in place, in different places, right? So you see like 1, 2, 3, 4, 5, 6, 7, 8 becomes 1, 2, 4, 3, 5, 7, 6, 8, and so on and so forth. And we can do that in log n parallel moves. So we can resort the position of these guys very, very efficiently. And this is the main mindset, the main compilation choice that a person has to go. So when I want to create qubits, curating entangling gates between this given set of qubits, how should I swap them and in a way that the gates are going to be applied in the most efficient way, in the fewest amount of actions. So let's take a look a little bit of a little more example here. So the way that we are operating right now is to create rectangular arrays also of the fixed sites. But by all means, maybe it's better to do hexagonal, maybe it's better to do something else. And we can, oh, boom, and put the guys in place. I'll do it again. Oh, boom. and then you drop the atoms over there. How do we do entangling? So entangling, as we were mentioning, it's something that requires atoms to be close to each other. So what we do is we bring atoms close, and boom, at that point, that's when we shine a laser light and we do the entanglement. That's the entanglement happening. Let me show you an example of this happening. Oops, I want my video. So this is a little bit of our own programs playing with that and rescrambling sets of qubits in a line. But this is just an example of the type of thing that you might be interested in creating, not just for visualizing, but also for allowing users to interact with it in an easy way. This is a moment for us to kind of tie back to the first example that I gave you, right? The example that I gave you of why this is interesting is that we have this 3D hypercube geometries. We were choosing this very specific code. I believe it's a color code. There's called 832, 8 qubits, giving 3 logical for error depth 2. And what I'm going to show you here is the actual operation of those for those logical qubits for 48. So for 48 in parallel, this figure or this video is not a simulation. Okay, this video, each of these dots is an actual atom. It's an actual atom. Okay, so this is the actual quantum processor processing. So let me, without further ado, just show you. So you see these guys moving, and then whenever they get close together, you see red ellipses showing that we shoot the lasers that lead to entanglement. So guys, move up, up, up. We just generated the 48 cubes, and now we are doing this parallel entangling operations between the logical qubits. And then now we go and we exchange to another set of 24, create the cubes, bring them together, and start doing parallel, what these are called transversal gates. These are gates that when you apply among logical qubits, you can achieve logical controlled 2-qubit gates by applying entangling operations individually in pairs of qubits, right? So you have a patch that corresponds to your logical qubit. You want to generate like a CZ between 2 logical qubits, but what you do is you do CZs between each pair of individual physical qubit, and that automatically generates a transversal, a logical CZ operations between the logical qubits. So this kind of parallelization is what lies behind all of this. And voila. So this is one of the examples of creating that entanglements that you were seeing before that led to those complex circuit sampling demonstrations. So let's go for a summary here. The features that you need to know. So single qubit gates between 99.9 and 99.99, all parallelized. So you can do this in multiple qubits all at once. 2-qubit gates at 99.5, they are position programmed, and you can do parallel applications on 10 to 100 qubits. We didn't discuss this in much detail, but the noise sources are also fairly understood. And it would be great to see visualization tools that enable users to make use of that noise, that knowledge of noise to, do conversion, erasure, and tailor their own error correction protocols, et cetera, et cetera. So this is a little bit of a summary of all the content on this, but we will not go into this in detail. And I wanna stop a little bit for an outlook. Okay, so today we are looking at physical error rates that are order 10 to the minus 2 in a qubit operation. And what we need to have large, very large scale quantum algorithms is 10 to the minus 15. Doing this with simple engineering of physical qubits is nearly impossible. Okay, and that's my euphemism way of saying impossible. So it's very, very unlikely that we'll be able to cover 12 orders of magnitude or more of performance by simply engineering and control and et cetera, et cetera. The only way of doing this, as we know today, is by performing error correction. But this is hard, and we need all breakthroughs possible, and we need things to really, really work at like highest possible performance. Neutral atoms are contributing a bunch of things. Of course, they're contributing neutral atoms. That's as we discussed. They are all equal, and they are repeatable and scalable, et cetera, et cetera. But putting together qubit shuttling, parallel operations, right? So where we have these logical patches sitting side by side and having single control entanglement operations, and zoned architectures, we believe that this is a big step forward on enabling this error correction, enabling error correction to increasing scale. We are hoping that you understand that and that you join us on this. It's an exciting time. We appreciate that this challenge is going to be very difficult. Many of you may not have gone through error correction, and the error correction is a highly mathematical and highly advanced topic, but you don't need to know everything about it, right? So what we are looking for is to enable users in all stages of advanced understanding to contribute to this co-design, to contribute to understanding what are the capabilities and requirements and features and possibilities with the neutral atom platform, and tie that to their algorithm design so that we can achieve demonstrations such as the one that I was looking at right now. And with that, I believe that my talk is done. And if we want to take a few moments for questions, I'll be happy to take questions.
Thanks so much for your talk, Pedro. Yeah, I'm happy to get started by giving you a few of the questions that were asked in the chat during your talk.
Yeah.
Yeah, so first, I'm sorry, I don't know how to say your name. Jabez asks, can gates be applied during transport or during the shuttling of the atoms?
So no, the gates, so atoms move, stop, gate, move. But it's not like, you go pass the ball, Ronaldinho takes the ball, already kicks before. That doesn't happen, okay? So you have to make the atom stop, and then you do the gate, and then you continue. That's the process.
Okay, fantastic. Somebody asked a question. I tried to answer it in the chat, but I figured I'd give this to you just in case anybody else had the same confusion. So somebody asked, so Niraj asks, for the permutation invariant gates, it looks like they create a global phase on each of the basis states. What's the difference
Yeah, it's not quite.
between?
Let's look at it again. Let me here. Let me share my screen once more. So notice that we have a system of 3 qubits, right? So these guys actually, when you think of it, like it's a state psi, there's going to be a linear superposition of all these possible states. And now you see that when you apply this permutation symmetric Z gates, this guy has a phase phi 0, these 3 guys have a phase phi 1, and these 5 guys have a no, 4 guys have a state phase phi 2. Sorry, 3 guys have a phase phi 2, and 1 guy has the phase phi 3. So if psi is a linear superposition of all of them, there are 4 distinct groups: the group of 0, 0, the group of 1, 1, 1, the group of 1 excitation, and the group of 2 excitations. And each of them gets a different phase, so it's not really global. I hope that answers it.
Yeah, that was great. Thank you. And anybody else, feel free to unmute and or paste more questions in the chat, and I'll make sure that they get asked. So next, Raphael asks, what is the way that you primarily communicate with the AOD? Like, what language do you use? You know, how do you program the electronics?
That's a very good question. Me, as not an electrical engineer, of course, don't have the answer to this question in advance, but I can try to pick up on what I have been hearing. Right. So definition of gates and like the gate level compilation. As far as I know, we are doing OpenCasm. Communicating with AOD, I believe that we do a mix between C++ and Python. Okay, so the cheap answer is all of your all that you mentioned, right? But nothing outside of that, yeah, that I know of.
Wonderful. So Raphael also asks, for the atom moving, how do you actually move the lasers around?
So the AOD, right? So it's the acousto-optical deflector that I was mentioning. So this guy is able to take one beam or a multiple of beams and make them like deflect in a given direction. So we get 2 AODs, one kind of vertical and one horizontal and one vertical. And now we control one to do this and the other to do that. And now, whoa, everybody goes together, right? But to do something like this, right, you start to need kind of more tones to control the system. So it gets very hard to control like a single one to do whatever you want. You do some of them, but that's a little more complicated.
So do you think that if people choose to do QuEra's project and then working on compilation, that this is something that would be important to try and figure out how to incorporate the fact that you can only sort of move in blocks together, or does
I
this
think so. Absolutely think so. And I'll be happy to add these slides to the GitHub repo so that you can. I mean, the rules are stated there, so you can just revise them.
That would be fantastic. Thanks. Yeah, I appreciate that.
Mm-hmm.
Chavez asks, can we bring together 2 lattices of atoms but only entangle selected qubits? So on your slide, it was suggestive that like when 2 blocks were brought together, the little circles appeared around the adjacent qubits to show that they were being entangled, but each pair of qubits was encircled. Could you, for instance, only entangle certain pairs?
So if I'm understanding the question, the answer is not today. Okay, so we are hoping and working on ideas for kind of local entanglement as well. But so you could, in principle, enable that as a a possible how do I say user design choice, right? Because we don't know exactly what's going to be the next generations of this. So you could definitely enable that as a feature, simply because it's a possibility. And if we figure out that we and the users, right, figure out that there are good reasons that they save a lot in compilation by doing that, then we can double down in our interest in enabling those kind of operations. But as the platform is today, it's all about distance. Okay, so if the atoms are close together, there's gonna be one big cannon here that's gonna shine on everyone. So if you're close, you got caught. Okay, yeah.
No, thanks so much for that answer. So Jarvis also asks, on the new architecture, could you explain the separation into storage and
Yeah.
entanglement areas? Why is it advantageous to have different areas for the function?
Yeah. Okay. So let's imagine this, right? Like I have a memory zone here, an entanglement zone here, and a measure zone here. The difference, so the entangling zone, what it has, you have to now look outside of the machine. What this has is a laser cannon that is aiming here, right? That is shining, that's gonna be shining a laser beam that picks up this entangling zone. But the memory zone doesn't have anything. The memory zone is just these guys, they are there. There's no laser, we don't have to do anything on that. And this allows also to create laser beams that are not as thick, right? So if we have a huge zone, creating a laser beam that is as thick as the zone is actually quite difficult. They are called top hat beams, and we use those for analog computing. But for creating like a thinner entangling zone allows you to not have to have such a wide beam and then being able to entangle in this area. The measurement zone is the same. There is a laser that comes that generates the excitement and the fluorescence that leads to the measurement process. So there's a matter of distance, positioning things far from each other. What do we have to actually control, and where are you aiming lasers for entanglement, etc. Those are some of the parameters that go into thinking why one area is better than the other.
Okay, that makes a lot of sense. Um, so Liam asks, so when you showed these diagrams, right, all of the blocks were sort of rectangular and that you could only address things in rows and columns. Is that a restriction of the hardware platform, or could you, for example, pick a block to move along a diagonal?
Wait a minute. Okay, no, I think we're skipping another of Liam's questions. Maybe there is something.
Oh, yes,
I'll
sorry.
be happy to answer that, but I don't want to miss the other one.
Of course. Thanks for pointing that out.
So maybe there's something basic I'm missing, but how do neutral atoms allow the implementation of error corrections that ions do not? So there are a few things that go into place here. I think that the most important part, so far, ion traps, they have mostly been operating in one dimension, not in 2D. Although I know that there are very reasonable new proposals for doing 2D traps. But the speed at which you transport atoms and the fact that you can turn the interactions on and off, remember that for ions, interactions are always on because they interact via Coulomb repulsion and the oscillations that they get from that. So you cannot turn those on and off. So any ion movement is by definition a little more sensitive than neutral atom movement. You add to that this high parallelizability, right? So the fact that you can take these two guys and bring them side by side and do these transversal operations. I think that some of this, the moving capacities and the parallelizability, oh my God, of operations are something that for ions are not as advanced as for atoms, and I don't know if they actually can achieve the same. And now we can go, Ben.
Yeah, sorry for missing the first question. Yeah, so the second question about addressing along just rows and columns, or the
Yeah.
ability to address along diagonals as well.
Yeah, so the rules are stated, right? It's like the Bible. The rules are there. So it's horizontal and vertical. We don't address in the diagonals.
Wonderful.
But notice that you can, in principle, right, go to like the storage zone and pick up two atoms that are in the diagonal and move them. Okay, that you can do. That you can do. But I mean, if you can control in the horizontal and vertical, then you can make things move diagonally as well.
Okay, wonderful. So Raphael has asked a question. I have to admit, I don't quite understand this question, but maybe you could talk a little bit about the process of readout. How do you actually read out the state of the atoms at the end of a computation?
Right. So the readout process is today destructive readout. Okay, and it's destructive not in the like in the quantum sense where you demolish the state. You demolish the whole atom. The qubit flies away. Okay, so what happens there is what you have an atom, and what atoms that are in the ground state, you can make them fluoresce. So you shine light, and it spits light back, right? But atoms that are excited, they do not. This happens at least between the ground and the Rydberg, and so whenever we are looking for doing measurement, we have to separate the states, and whatever state is excited pretty much is going to fly away from your system, and states that are not excited, they stay in your system, and they're going to shine. So actually, when you have the three qubit, the three state system, I have to confirm, but my understanding is that pretty much you have to promote one of them. So ones get promoted to Rydberg before you try to measure, and then you can separate what's zero and what is one. But that's my guess, right? So whenever you are measuring atoms, so you're looking at fluoresce versus not fluoresce. And not fluoresce means you are looking for a dark state, and nothing is darker than an atom that is not there. So that's one of the reasons why we make the atom fly, right? We let them go away, and then you know that whatever is zero, whatever is one. There can be measurement errors, but that's the process. And the signal, it's all goes to a camera. Okay, it all goes to a camera, and this camera, you know, there are many things that we do to collect information fast or slow. I don't think that I can give you details about how that works. We have some smart things that we do.
All right, thanks so much for that answer. Next, we have a great question from Niraj, who's asking about T1 errors in the hyperfine manifold. He says similarly to you see decay in superconducting qubits is something people are very familiar with dealing with. What causes T1 errors between the hyperfine states, and how like dominant is that process?
That's a highly technical question. I know that the Rydberg state is highly sensitive to black body radiation. I'm not positive I know the good answer for what are the main factors that lead to decay on the hyperfine manifold, right? So quite often, just the fact that we are holding atoms with a tweezer means that you can always pick up a photon and something can happen there. Okay, that's the reason why we use this magnetically neutral state, this MF equals 0 that I was telling you about. So that's the guy that's going to interact the least with the fields, and you can see that the decay. I mean, we have coherence times of 1.5 ish T2s at least. I I don't know if I have a better. Actually, Ben, let me put you on the spot, right? You have thought about this a little. I don't know how much you have thought about hyperfine, but are you aware of anything that I am not right now?
No, I think so yeah, like you said, when I was working with the device, it was all with
Ground Rydberg.
Rydberg states.
Yeah.
Yeah, ground
Okay.
Rydberg and
Yeah.
different dipole selection rules as well. I don't
Yeah.
know if yeah, I really don't know about the hyperfine states.
So my suggestion then, Raj, is to go through the reference over there, and also join our QuEra public Slack. I think that Ben will add a little link if he has not already.
I posted a link earlier in the in the chat.
Okay. So you can join there and ask these questions. Any of the questions that you feel my answer is not thorough enough, you can ask there, and I will be able to look for the answer offline.
Wonderful. All right. So another great question from Niraj. So when you're moving the atoms, do you have to be worried about them accidentally colliding and interacting with each other?
So I think that the answer to this question lies on this figure here, right? I mean, roughly none. I don't know if I can say more than that. Right? Like if the atoms are not moving, on performance. If the atoms are moved, roughly the same thing. So probably there are some, but I think that nothing really, yeah, that's probably not the key, the main source. David?
Yeah, hi Pedro. Thank you very much for your workshop. It already clarified a lot of details. But one thing, so after reading Dolev's paper and watching his lecture on logical quantum processor, it seems like we should pay a lot of attention to error correction, as you said. But like you slightly mentioned it, and this paper and reading through the assignment confused me a little bit. So, for example, should we thinking about logical gates in terms of error correction codes? And for example, should we think about implementing CSS codes in this perspective of error correction and how it relates to a global thing?
No, you don't need to. We're not expecting you guys to create any error correction codes or anything that complicated, as much as creating tools that enable people to do it when they want with the appropriate amount of time, right? So I think that learning a couple cases how to do it and making sure that your tool works for those cases can only be a good exercise. But yeah, I think that I don't know if this answers your question.
Yeah, I mean, should we pay more attention for error correction perspective?
So at the end of the day, what we are looking for is to enable people to encode error-corrected protocols as easily and as fastly as possible, and to figure out if those encodings are performant or not given the hardware constraints. Okay. I think that's how I see it, right? So depending on the protocol that a person chooses, a given error-corrected logical qubit, you will be able to have different types of transversal gates. Not all gates are going to be transversal, not always. Sometimes those gates are Clifford, sometimes they are not. And figuring out what's the best way of doing this might even be dependent on application. Okay, so we really don't know so far. And so that's what we are trying to push ahead.
Okay, thank you.
Wonderful. All right. Well, are there any remaining questions? I don't see any more in the chat.
So the arrangement of atoms on the fixed lasers can be arbitrary, right? The limitation to a lattice arrangement that can be scaled is only limited on the movable lasers. as if I'm understanding what you're asking, I think that the answer is correct. Okay, so you could put the fixed atoms on a hexagonal lattice, and then displace things around with the other rectangular one that can be scaled up and down, etc. Is that better or worse? Hard to say, but who knows?
There are some limitations to the atom arrangements, right? Like the addressability is done by a column of lasers.
Yeah, absolutely. I think so. I mean, the addressability is always gonna be kind of like in the readout layer, right? So you saw that the readout layer is like a extended kind of rectangular layer, a region or zone, and then you just shoot a big laser over there. Yeah, and then everybody that's in parallel about, I think that the Harvard demonstrations were for their 60 entangled qubits in parallel, at least on the 99.5 to qubit gate fidelity experiment.
Incredible. Okay, well, unless there are any more questions, Pedro, I'd like to thank you so much for your time. We really appreciate you giving this workshop. And yeah, anybody who has further questions, feel free, like Pedro said, to join the QuEra Slack channel and ask them there. Thanks so much for coming. Yeah, thanks so much for coming. And
Thanks for the invitation. Thanks for arranging this. I think that this is a very exciting event, and we are really hoping to see a lot of people trying what we are bringing up. We know it's going to be challenging, but that's the whole point. And thanks again for having me, Nas and Ben. So have a good one.